Hey everybody, it's Mr. Molikash again, and today's video has to do with arc length of a smooth planar curve and distance traveled. And we're going to start by looking at just a random graph. We'll just take a look at a just general f of x curve from A to B. So we'll have y up here and x over here. Okay. The area, of course, in this region between the curve and the x-axis on this interval, right? The area is found by summing together a bunch of really thin rectangles. And if the rectangles have a finite width, we call that a Riemann sum, right? But the integral from A to B is actually the limit as those rectangles get super thin and approach a width of 0. We're adding together a bunch of y values, right? And the y values are the f of x values. And the thickness of each rectangle, or width of each rectangle, would be the dx, right? And so you're adding up a bunch of those really, really thin, approaching 0 thinness, right, rectangles, and then you know, that's the way that we get the area under the curve, right? But today's video isn't about area, it's about length. It's about how long this curve is. All right, so the length is also going to be adding some things together. Okay, and what I'm going to do is maybe use black. Okay, let's use black here. And we'll take a look at just one little piece of this, maybe just this little piece right here. And we'll call the width of that piece the dx. Okay, so that little piece from here to here, we'll call that dx, right? Okay. Well, from here to here, that's the change in y values, right? So we're going to call that dy. And so you can kind of think about, if we just blow this up really big, it's if we make this small enough, this curved piece will actually be locally linear. It'll look like a line. Okay, so we have our dx here and we have our dy here. Of course, dx is approaching 0. Dy may or may not be approaching 0. But we're going to try to find out what the length of this little piece is, right? What the length of that little piece is. And the way that we can do that is by using the Pythagorean theorem, right? So dx squared. Now, technically, I'm doing some hand waving here. If a mathematician is watching this, please forgive me for the hand waving. This is not super mathematically precise. Technically, this should be delta x and delta y, and then I'm going to take the limit later, but this still works for our purposes, okay? All right, and then to find out what L is, of course, I have to do the square root of both sides, right? Okay. Okay. But I need to calculate an integral with a differential of dx, right? Okay. So what we're going to do with this expression is I'm going to put this in here as dx squared plus dy squared, but I don't have a differential out here. I don't have this differential, and I need it, right? I need to calculate the integral with respect to x, right? So in order to do that, I'm going to multiply the outside by dx and divide also by dx. And I'm going to try to put this inside this square root. Okay? I'm going to do that. So how do I do that over here? If I divide all this by dx, right? Well, I can put it under the square root by extending the square root down and squaring the dx. The square root of dx squared is just dx, right? Now, by doing that, we can simplify this expression here. Dx squared divided by dx squared is just 1, right? And then dy squared divided by dx squared, well, that's just dy dx squared, right? And so this is the arc length formula. This is the length of that little tiny piece right there. It's just one of the lengths. And we're having to, again, this whole thing is these little lengths, and we're summing all those lengths together from x equals a to x equals b. So the integral is finding the length of this entire curve, all the little lengths of those hypotenuses of those little triangles, and they're tiny, tiny triangles, where the dx is approaching 0, will give us this length. Okay, so there's your formula. Write it down, memorize it. You're going to need to know this for BC calculus. Okay. Now, let's look at a specific example. And by the way, you will not ever have to work this integral out by hand. Okay, but let me just give us some expression, right? Let's just say that we have, f of x equals whatever this is. Maybe this is x cubed, right? Maybe this is x cubed, and it's not, but just say for a moment that it is, right? The length of the curve then, the length of this curve would be the integral from a to b of 1 plus 3x squared with respect to x. Now, this is a very, very difficult integral to work out by hand, so you would just use a calculator to do this. Okay. All right. So that's the that is the length of a curve part. Now, what do we mean by distance traveled? Well, back in AB calculus, you may have learned about rectilinear motion. What that means is that motion occurring along the x-axis, right? Occurring along the x-axis. So what we're going to do now is just kind of look at maybe a particle that's moving along the x-axis over time. Okay, just the x-axis. So here's the x-axis, and x is going to be a function of t. So maybe we can just call this x of t. Okay, and x of t is a position function. So x of t would be telling you where a particle is along the x-axis at a specific point in time, right? And here we go with the crazy, I pressed too hard on the screen. But, maybe this is going back and forth, back and forth, back and forth, right? Okay. Not a problem. We can just go to another page. Okay. Oops. Not that kind of page. That kind of page. There you go, Mr. Molikash. How you doing? All right. All right, so, let's say that a particle is moving along the x-axis over time, given by this function, 2t squared minus 3t plus 1. And we want to find the distance traveled. Over the time interval, let's say from 0 to 2 seconds. 0 to 2 seconds. We would play the same game, right? You would find the distance traveled would be the integral from 0 to 2 of 1 plus, this would be x prime of t squared dt. So what would we put in the place of x prime of t? Well, that's pretty easy to do if you know your derivative rules, right? This would be, what, 4t minus 3. Okay, and that would be your integral. And then you would use a Desmos calculator or something like that to do the integral. Okay, so there's the arc length of a curve and the distance traveled, there are some delta math problems to do, right? Here's one of them. I'm trying to get that purple back. Yeah, it's close, close. Okay. So here's an example, right? It says write the integral expression that will give the length of the path given by f of x equals -9 natural log 8x plus 1 from x equals 2 to x equals 3. So immediately I know I have to put 2 and 3 in for my a and b, right? I have to do that. And because this is a length of the path problem, I have to do a square root. Whoops, not there. I have to do the square root in my integrand, right? I have to do the square root, and this is going to be 1 plus something squared. Okay, what goes in that little gray spot? It's the derivative of this. So I got to figure out what the derivative is, and then just put it in that set of parentheses, and then I should be good, right? So it's going to be -9 times 1 over the expression, and then don't forget the chain rule, right? We're going to have to multiply by 8. Now, I don't think I have to simplify all this. I can just put all that in there and it'll give me credit, but just, I'm going to go ahead and simplify this. This should be -72 over 8x plus 1, and I just multiply the 8 and the -9. So I'm going to go ahead and stick that expression there in parentheses. Okay, and I'm going to go ahead and submit my answer and get the green check mark. So find your derivative, stick it in that set of parentheses, make sure you do 1 plus the derivative squared under the square root along the given interval. Pretty easy stuff, right? Okay. There are other ones where you have to find a length of a boundary, right? So this one's just going to be 2 arc lengths, right? You're going to have to find the intersection of these two curves to find your a and b. You can do that using Desmos calculator, right? Set this equal to this and find your a and b. And then you're going to have to find the length of the top curve along that interval and the length of the bottom curve along that interval. And it wants you to actually do the integral, right? Well, the good news is we can use Desmos to do this, right? So let's go use Desmos real quick. Use the College Board Desmos and go ahead and put our 4 sine x minus 4. So let's go ahead and put our expressions in. There's our top curve, and then the bottom curve is going to be -3x to the 8th plus 3. Okay, and we can get a better looking graph here by zooming, with our fingers. Use the fingers along the x and y axis to zoom things, right? All right, so we've got our a and our b. Make sure you don't grab the 0 of the function. We want the intersection there, right? Okay. Now, slick trick, you can actually export both of these points to the expression list, and you can go ahead and copy and paste these numbers for your a and b. So there's going to be your a and b. We're going to need 2 integrals, right? We're going to need 2 integrals here, one for the top length and one for the bottom length, right? So I'm going to copy all that and put it down here, and I'm going to add these answers together, okay? So square root 1 plus something squared dx. The something that's squared is going to be the derivative of this blue curve. And the blue curve, let's see, the derivative of that would be -24x to the 7th, right? Okay, so there's the length of the top curve along the interval. And then the bottom one, same thing. And so what's the derivative of 4 sine x minus 4? I think it's 4 cosine x, right? All right, and so our answer is going to be this number for the length of the top, and then the length of the red stuff on the bottom is this. definitely does look shorter on the red side, doesn't it? All right, and then we're going to round off to 3 decimal places, so 22.965. I think it says 3 decimal places here, doesn't it? Yep. Okay. So, they'll do the same thing that I just showed you in Desmos. Of course, you have to find the intersection using a graphing calculator. Find the derivative of each curve, find your arc length on that interval, add them together, done. All right. Last thing is we're going to do a distance traveled problem. And it says find the total distance traveled. The graph is shown in the figure. Find the total distance traveled by the particle from 0 to 18, right? So the way that you're going to do this is you need to do your integral from 0 to 18 of 1 plus x prime of t squared dt, right? And this is a graph of x of t, right? This is a graph of x of t. So we would need some information about x prime of t to do this. Right? So what you need to do is kind of find out what's going on with the derivative. Right? So we're estimating this distance traveled by looking at where these extreme values are. There's a minimum at -5. There's a maximum up here at +4, looks like. And then there's a 0 down here, right? So the x of t graph is telling us there's a change of 9 units along that 2-second interval, right? It went 9 units one direction, and then it went from there to there. It went 9 units in another direction, and it went from here to here, and so that's the total distance traveled, right? Probably going to change this to make sure that you actually have an expression for x of t rather than having to use the graph. So in this case, like if you have an expression for x of t, you can actually compute this without having to estimate things, right? So you're going to do the integral from 0 to 5, square root 1 plus derivative squared. And what's going to go in here is the derivative. I'm not going to compute this. I know you know how to figure out how to numerically calculate this integral. So you just go do this in Desmos calculator, right? Go do that in Desmos calculator and round off, right? So that's kind of how you would do that problem. But I'll try to make sure that you only have expressions for x of t rather than just using the graph. And that's it for today. So happy Friday. It is Friday the 13th as I'm posting this video. So you have a great Friday the 13th.